60 degrees of slope characterizes the steepest cable car ever built in the world. Why is such a vertical angle necessary in the freezing Swiss Alps? To the casual observer, the cliffs rising almost straight up seem impassable, but this trajectory allows the system to be pulled almost vertically up the rock face, bypassing the impossible terrain. A massive transportation system hangs suspended in mid-air here, held in place by only a few steel cables stretched across kilometers of open space. But this is just the beginning. Workers suspend themselves thousands of meters above the ground to assemble the hidden mechanisms behind the scenes. At first glance, the process looks like standard assembly, but in reality, they install each pulley and bolt while hanging in the void. One can notice how the workers maneuver with heavy tools to secure the steel cables against the sheer rock. Even the smallest mistake on this slope leaves no second chance. The conditions demand absolute precision from the crew at every moment, as extreme engineering feats are made possible only through such calculated risk. It gets more complex further on. The structure solidifies into a functional route ready to operate. 159% is the maximum gradient achieved on the route of the Steckelberg-Muren line. Located in southern Switzerland, this system operates in one of the most rugged mountain areas in Europe. Two cabins move along the cables, each capable of carrying up to 85 passengers. The line stretches over 1.1 kilometers, climbing nearly 800 meters in elevation. Why do engineers push technology beyond traditional limits with such an extreme incline? It would seem easier to choose a different path, but the terrain dictates strict rules where very few transportation systems in the world have attempted to go. One can notice how the cabins rise almost vertically against the rock face. Engineers operate this suspended system amidst fierce winds and heavy snow. At first glance, the lift seems simple, but in reality, even the smallest mistake is not an option here. The equipment gradually overcomes the elements, but this is just the beginning. It is visible how the structure holds firm. The journey continues upward, 60 degrees of incline. This is the extreme angle engineers chose for the new cable car trajectory. This figure represents a bold engineering decision, but it is the only design that truly fits the difficult terrain at the final destination. Why is the design stage on paper considered the most critical phase of construction? It would seem that the physical work on the mountain is harder, but without the initial calculations of experienced engineers, even a tiny error on the drawings could make the entire system unsafe to operate later. Every factor that could affect the system undergoes rigorous mathematical modeling, from the steepness of the cliff and the height of each tower to extreme wind forces and cabin loads. Calculation covers everything down to the smallest vibrations as the cabin moves and the precise tension of the cable. This is not a job for ordinary engineers, but for highly seasoned specialists who understand that paper drawings determine the fate of the project. Immediately after the drawings are finalized, the focus shifts to the construction site situated thousands of meters above sea level. Here, solid bedrock is exposed, the terrain is extremely steep, and natural flat ground is almost non-existent. To make construction possible, the team must use controlled blasting to carve out a flat foundation. Engineers calculate exactly how much rock needs to be removed and determine the precise amount of explosive energy required to lower the terrain to the design level. Drill holes are arranged in a specific grid, spaced from just a few dozen centimeters to over 1 meter apart to ensure even breakage. One can notice how the dust slowly settles after the blasts, which are triggered in sequence rather than all at once. This sequential detonation allows engineers to control the force and prevent cracking in the surrounding rock mass. After the dust clears, all broken rock is removed and the surface is leveled to prepare for the foundation. The load-bearing capacity of the ground is thoroughly checked to guarantee stability. Only when the foundation reaches the correct elevation can the project move to the station construction phase. But this is just the beginning of the logistical challenges. At an altitude of several thousand meters, there are absolutely no access roads for trucks or large cranes to deliver materials. As a result, the team must build a temporary cable car system solely for transport. Building this temporary line takes considerable time, but it functions much like the main system will. It acts as an aerial logistics system where each trip can carry between 1 and 3 tons of materials, depending on wind conditions and the length of the cable span. Steel beams, cement bags, formwork, and even small machines are secured to pallets and suspended beneath the cable. The camera glides along the steep cliff faces as the loads move slowly across distances stretching hundreds of meters. Each trip typically takes 20 to 40 minutes to deliver materials to the site over the sheer terrain. Every lift requires careful planning around load limits, because at this altitude, strong winds can cause suspended loads to swing dangerously. Now the construction of the cable car station officially begins with the setting of the building's centerline. The team defines the foundation zones and main load-bearing points with absolute precision. Foundations are excavated and drilled deep into the bedrock, where steel anchor rods are installed to firmly tie the structure to the mountain. Once the foundations are secured, reinforcing steel is installed exactly according to the drawings to form the framework. Concrete is then poured in stages, with strict control of time and temperature to achieve the required strength. At first glance, pouring concrete seems like a standard procedure, but in reality, under cold mountain conditions, even a slight drop in temperature can compromise the structural integrity. After the concrete reaches sufficient strength, the formwork is gradually removed to reveal the beams, floors, and load-bearing walls. On top of this concrete skeleton, large steel bases and support frames are installed to prepare for the cable system and sheaves. All elevations and tolerances are carefully adjusted because at several thousand meters above sea level, repairs are extremely difficult. The station then moves into the exterior cladding phase. Metal panels and glass are installed to shield the building from strong winds, heavy snow, and ice. This outer shell acts as a protective barrier that allows the station to operate reliably in extreme conditions. Next, the process moves to the steel cable manufacturing plant, which serves as the heart of the entire system. Here, high-strength steel is drawn into thin wires with precise diameters before being wound onto large spools. Multiple small wires are twisted together in a predefined pattern to form cable strands that can withstand enormous tensile forces while remaining flexible. One can notice how the machines rotate ceaselessly, maintaining continuous control over the tension of each wire. This ensures that the load is evenly distributed throughout the cable structure. After twisting, the cable passes through pressing, compacting, and geometric adjustment systems to stabilize its internal structure. Some cables are also lubricated or coated with protective layers to reduce friction and resist corrosion in harsh environments. Finally, each massive cable reel undergoes strict testing for strength, elongation, and dimensional accuracy before leaving the factory. Transition to the next level involves transporting these massive components to the site. The steel cable reels are loaded onto heavy-duty cranes and firmly secured on specialized low-bed trailers, as each reel can weigh several tens of tons. Trucks move at controlled speeds along pre-surveyed routes to handle the extreme weight. Drivers must navigate narrow roads and sharp turns as they approach the mountain area. Even though the factory was only about 40 human orders from the construction site, the transportation process took up to a week. Simultaneously, the cable car tower components are being manufactured in a separate factory. Instead of being built as a single piece, each tower is produced from multiple individual steel modules fabricated with high precision. Every section is machined and pre-drilled for bolts to ensure that all parts fit together perfectly. Afterward, these modules are transported to the base of the mountain for staging. Because the terrain is inaccessible to vehicles, each tower section must be suspended beneath a helicopter and flown to its installation point. At the construction site, the tower is assembled from the ground up, with each steel module carefully lowered into position. Once in place, every module is secured using hundreds of high-strength bolts tightened to precise torque values. The construction team measures and adjusts the vertical alignment using specialized surveying equipment before the next section is added. It gets more complex further on, as even a small misalignment at the base can be amplified dramatically at full height. Once the tower structure is complete, the installation of cable support frames and roller assemblies begins. These assemblies, weighing from dozens to hundreds of kilograms, are lifted into place one by one. Their position must be adjusted with extreme accuracy so that the steel cables can pass smoothly without excessive wear. Next comes the cable pulling process, which does not begin with the main cable itself. A smaller, lighter temporary rope is first lifted into the air using a helicopter or pulling equipment. This rope is guided through the towers to create an initial path. Using this temporary line, the team gradually pulls in larger and heavier ropes, step by step increasing size and load until the system is strong enough to pull the main cable. Once the main cable enters the line, high-capacity winches at the station control the pulling force uphill. Braking systems at the opposite end prevent the cable from sliding or sagging excessively. Throughout this process, the cable must remain suspended in the air without touching the ground or rock face. The pulling speed is extremely slow and continuously monitored because every meter of cable carries enormous loads. When the cable reaches its full length, both ends are brought together for splicing. Workers move along suspended work platforms hanging high above the ground, protected by safety nets. Here, the steel cable is kept under controlled tension while it is straightened and untwisted. The two ends are brought together for manual splicing, a process that requires exceptional precision. Workers carefully separate each bundle of steel wires and interweave them according to a predefined sequence. This creates a continuous loop with no mechanical weak point once the cable is placed under tension. Next comes the cabin manufacturing process, carried out entirely in the factory. The cabins are custom designed for each route based on load capacity and local wind conditions. Frames are manufactured from aluminum alloys and lightweight steel to provide strength while keeping weight low. Exterior panels, flooring, and safety glass are installed directly onto the structure. Before leaving the factory, each cabin undergoes inspections to verify sealing and operational safety. Only after meeting all standards are they packaged for transport. In areas without road access, the cabins are lifted by helicopter to the installation points. Before being mounted, each cabin undergoes a final inspection of its suspension system. The cabin is then attached directly to the cable, requiring precise alignment to ensure proper balance. Once mechanical installation is complete, the electrical and control systems are integrated. Power cables, sensors, and communication lines are routed to connect drives, brakes, and safety devices. Control cabinets are assembled to manage speed, acceleration, and safe stopping. All systems are carefully tested to ensure reliable response. At the heart of the system lies the drive unit, consisting of high-power electric motors and large drive sheaves. This unit transmits torque directly to the cable, operating smoothly under heavy loads. Finally, the system enters the testing and commissioning phase. The line is run without passengers to check cable tension and drive performance. Gradually, test loads and empty cabins are added to simulate real conditions. Engineers monitor vibrations and wind behavior to ensure everything performs within design limits. Thus, the cable car is officially approved for passenger service. Thousands of components unite to form a single functioning cable car line. The timeline spans from initial design drawings to the final system launch. This is an extremely complex process, covering massive project stages in a strict sequence. At first glance, the work appears finished, but in reality, technical insights determine the success of the operation. But this is just the beginning. Why is the transition to the active phase so critical? Testing reveals any deviation from the plan. This ensures that the system functions exactly as designed. One can notice how the cabins glide smoothly along the track. The equipment gradually takes on the full load. Accuracy is required to integrate every detail of this massive project. It is visible how the mechanism maintains constant tension. The system is ready to work.